So let's talk about differentiability. Now, in Calc 1, all you really needed for a function to have a derivative at a particular point is that this limit existed. Once that limit existed, we said that, hey, the function is differentiable at that point, and here is the derivative at the point. You define it by this limit. Well, in functions of more than one variable, the story is not so simple. In fact, you could have the limits existing, but the function still not be differentiable, and we'll take a look at an example like that. So we can look at differentiability of Calc 1 in another light using this epsilon. Let's define epsilon as the difference between here's the slope of the secant line, and here's the slope of the tangent line, right? The derivative gives you the slope of the tangent line, and this here is the slope of the secant line. Now, if the function is differentiable, and hence you have this equality here for f prime, well, the slope of the secant line should be equal to the slope of the tangent line, right? As delta x goes to 0. So this h could be thought of as just this delta x, and we expect that the limit of epsilon as delta x goes to 0 is also equal to 0, basically telling you that as delta x goes to 0, the slope of the secant line should approach that of the tangent line. So that works. We could rearrange this equality here, and by just multiplying by delta x and rearranging terms, we have delta y here given by f at x plus delta x, which you could think of just h minus f of x, is equal to this term here. And we could think about differentiability as the fact that the delta y goes to 0 as delta x goes to 0, and hence so does epsilon. Okay, so it's another way of thinking about differentiability, which is equivalent for Calc 1, but not, which is equivalent to the limit existing in Calc 1, but not necessarily so for functions of more than one variable. So with Calc 1 motivation in mind, here is how we will define a function to be differentiable for, say, functions of two variables now. The function fxy is differentiable at ab, provided that the limits exist, but that's not enough. Okay, so first we need that the limits exist, and the change delta z equals this term here, where epsilon 1 depends on delta x, epsilon 2 depends on delta y, and that these epsilons go to 0 as delta x and delta y go to 0. Okay, so looking back at this as a motivation, we now have, since we're dealing with functions of more than one variable, we have f sub x, f sub y times delta y, delta x, and we also have these extra epsilon 1 delta x. Okay, so the function is differentiable if two things are true. One, that the limit exists, and that was good enough for Calc 1. But for functions of more than one variable, it's not good enough. We also need to have that delta z is equal to a term like this, where delta z is given here, and that these epsilons go to 0 once delta x and delta y go to 0. So for a little more intuitive idea of the definition that's less formal, take a look at this equation here. What you're seeing here, what this equation is basically telling you is that the tangent line gives a fairly good description of the function when you're close to the point where you're evaluating the derivative. Okay, so the tangent line is you get the slope of the tangent line from the derivative, and that the linear behavior, in the sense of delta x, distance away from the point where you're evaluating the derivative, is proportional to the changes along y of the function, except that we have this additional error term, if you will. This term here quantifies the failure of the tangent line to describe changes in the function, okay? So this is the failure of the function being linear, basically. Okay? We want that to go to 0 as delta x goes to 0, okay? Because you're getting closer and closer to the line, and so that the derivative becomes better and better, and the tangent line becomes a better and better approximation to the function. You could generalize that thinking towards functions of more than one variable, okay, where now we have a delta z, and later on we'll see that this term here actually is related to the tangent plane, okay? So if this term here is associated with the tangent line, this term here is associated with the tangent plane, and this is basically the errors of treating the function as a plane, okay? So this is the failure of the function to be linear, and that these terms, these epsilons, go to 0 as delta x and delta y go to 0, is basically telling you that as you get closer and closer to the plane, to the point where you're evaluating the derivative, the tangent plane should become a better and better approximation, okay? So what did we buy ourselves with this definition of differentiability? This theorem, okay? So if a function is differentiable, it should be continuous, and that's pretty intuitive. I mean, we have that for Calc 1. So functions differentiable, it should at least be continuous, right? So here we have differentiability implies continuity, and here's the proof of that. Because we have differentiability, we have that the limit of delta z goes to 0 as delta x and delta y go to 0, okay? That's just coming up from here. These terms would then go to 0, and these terms would go to 0, so delta z would go to 0. But on the other hand, delta z is equal to what you see here, and so let's evaluate the limit of this function as xy goes to ab. If we get that it's equal to f at ab, then we know the function is continuous, okay? Because that is how you talk about continuity, that the limit exists and it's equal to the function. So here we have the function. The function could also be written, we could rewrite this as delta x and delta y going to 0 for this term here, okay? So we start at a, and we have this delta x rather than just x approaching a. It's just a way to rewrite the limit there. But what is f of, what is this term here? Rearrange using this equation there, you get that it's equal to delta z f a b. Now, because of differentiability, we have that this would go to 0 as delta x, delta y go to 0, so that's 0. And we have that the limit of the function as x, y approaches ab is equal to fab, which gives you continuity. So differentiability, in the way that we defined it, implies continuity. So let's take a look at a function in which the limits of the partial derivatives, right? So that f sub x, the partial derivative with respect to x, and f sub y will both exist. So the limits exist, but the function is non-differentiable, okay? Something that won't happen in Calc 1, but can happen when dealing with functions of more than one variable. So we have here this function. We define it this way so that it's 0 at the origin, but equal to this expression away from the origin. Let's compute f sub x at the origin using the definition. So this is straightforward just from the definition. we plug in these values into the definition, and we get that the partial derivative with respect to x at the origin is 0. Likewise, we do a similar thing with y. And notice here, since we are not at the origin at this point, since h is greater than 0, it's approaching 0, but it's greater than 0. We just take, so x is 0, and here is 0 plus h for y, so y needs to be h, and that's where we're getting this term here. We're plugging in the values into this guy. Minus f00, what's f00? Well, it's 0. And so our limit turns out to be 0. So the partial derivatives exist, and they are 0. Both x and y, their partial derivatives are 0 at the origin. On the other hand, this function does not have a limit at the origin. The limit does not exist. And if the limit doesn't exist, it's not continuous. And if it's not continuous, it cannot be differentiable. Okay, because differentiability implies continuity. So if it's not continuous, then we know that it can't be differentiable. And how do we know that this function does not have this limit? Well, we just do the two-path test. Okay, we're going to take paths with basically lines of slope m. And we plug in those paths, take the limit as t goes to 0 so that we get to the origin, and we get this expression here. We could try this for two different m's, m equals 0, which just basically means that you're approaching along the x-axis, and m equals 1, you're approaching along the line of y equals x. And on the one hand, one limit gives us 0, the other limit gives us 3/2. Two different values as we approach by two different paths means what by the two-path test? That the limit does not exist. And again, the limit not existing implies the function is not continuous. The function not continuous implies that the function is not differentiable. So what's the moral of the story there? Even though your limits can exist for your partial derivatives, it does not mean the function is differentiable. So then how can we have sufficient conditions in order to show that a function is differentiable? Well, we have this theorem here that gives us the conditions of differentiability. So suppose the function f has partial derivatives, so these limits exist, defined on an open set containing ab, with fx, here's the crucial part, that these partial derivatives have to be continuous at ab. So if you get that fx and fy are continuous at the point ab, then you know that the function is differentiable. So not only does the limit have to exist, but that these have to be also continuous. And once the partial derivatives are continuous, then you could have the function being differentiable. Those are sufficient conditions for the function being differentiable. And what you're seeing here is the function that we looked at, in which the partial derivatives existed, but it did not have, it was not differentiable. So here's that function. It's not differentiable, although the partial derivatives exists along the y and x axis, and they are equal to 0. So both partial derivatives existed, but the function is not differentiable.